Hey, looking at my smartphone here. Actually, this serves a purpose. I'm not just distracted by my smartphone, as might happen occasionally in class. This is a stopwatch. I'm going to try to stick to my 10-minute target for this rapid review series, because that has been my goal all along, and I have not quite delivered on that goal for you or for me. Let's see what happens today. Our reward, if I get done early before 10 minutes, is I have a bonus topic for you. So let's jump right in. Pulleys is the topic today. We're going to talk about how pulleys can be analyzed in terms of their forces and accelerations. Here, there's a system. I have a system of lab masses and a pulley rig and some string. I'm going to call that system, I'm going to define that system to be the two masses plus the massless string, and they're all working in unison. They all work together. So in general, a system is something that is a collection of objects. Right up until now, we've said the object has a force on it. Now we're going to say the system has forces on it, okay? So back to our system here. As always, even for a system, F net is mass times acceleration. So Newton's law applies if you have a system, just like it would for a single object. Okay, so when we want to analyze a pulley system, we first have to choose a direction for plus. And you might say, plus what? What are you talking about? I mean, plus everything, right? It's a coordinate system. We're setting it up arbitrarily. You can choose plus any direction you want. Once you choose it, you have to stop. So you have to stop choosing and analyze using that coordinate system consistently for the rest of your problem-solving session. Okay, so if we look at the picture here, I've arbitrarily decided that plus means mass 1 is moving to the right, which of course means mass 2 is moving down because of the way they are attached. So that is my plus direction. It means everything after that, velocities, accelerations, they all fit in that system and make sense. Okay, so I can say F net is mass times acceleration for the system. And it's sometimes handy to use the word causing and opposing. If you want to talk about forces that cause the system to move in the plus direction, then you can use that vocabulary. You can use opposing if you want, which is causing it to move in the negative direction, right? So you can say that, or it's opposing motion in the plus direction. Do you see why the directions are so important? Because cause and oppose have everything to do with the plus direction that you've arbitrarily defined. If you look at the picture, I chose to define plus as down for mass 2, and I did that because looking at the picture, I could be pretty sure that the way it wants to accelerate is in that direction. Positive acceleration, mass 2 falling and going faster and faster. In some problems, it's not going to be so obvious, and that's why I say you can choose that direction arbitrarily. If you had a mass, if you had a table and a mass hanging from both ends with two pulleys, it might not be obvious when the problem is stated which way that system would move. And so you would just arbitrarily select a definition for plus in your coordinate system, and everything else will follow correctly. One of the things I like about physics, it always works out. I got to define one other word is internal. The string is internal to the system. So there's no, it doesn't fit into the equations in any way. It's just part of the system, just like all the molecules in M1 and M2 are part of the system. You don't analyze that. Later, I'll make a comment where you can get that tension force, but it doesn't fit in if you're analyzing the whole system. So if you look at the equations that I've shown here, you'll see that for this system, as I've sketched it out and labeled it, this equation is true. It's essentially saying F net is mass times acceleration. Now, you already know how to take that kind of an equation, and if I give you 2 or 3 of the variables, what their values are, you can solve algebraically, punch in the numbers, manipulate the numbers, and get an answer numerically. Most students in my classes are super comfortable with that. Where you begin to move into more advanced thinking is when you start solving algebraically. So I'm going to use this equation here as a platform to show you what your study of physics might look like in the future as you go into more advanced study. Rather than plug numbers in at the very beginning of a problem, you wait till the very end to put your numbers in. Everything else is done symbolically and algebraically using symbols. Let's check it out. You might be asked in advanced class, what mass would you need to prevent this system from slipping? And if you freeze the video, you can see the details. But important here is the form of my answer. I say, for no slipping, just make sure you choose M2 appropriately. It's got to be less than mu static times M1, and you're good to go. Or you're good to not go. It means you will not be slipping if you meet that condition. Here's another question you might be asked. Same system. I'm going to use the same equation in the box to derive another answer that might be asked. What would mass 2 have to be to get this system to move at constant speed? And you can see again, I can choose that mass appropriately and watch that system move at constant speed. One more, here's the most complicated one I could think of. What's the acceleration of this system moving? So you're given that the system is moving. We can't assume constant speed, so we take the general case of acceleration being non-zero, and we solve, and we find out that the acceleration will be this value. Wow, that looks complicated. But what's good about it is I only have to solve the problem once. I can solve all kinds of problems like this, find out the acceleration. If the mass gets changed, if the coefficient of kinetic friction or whatever changes, I can use that equation to solve it. One handy thing too, by doing this, is you can look for special corner cases. For example, if I look at this term in parentheses, if M2 is the same as mu k times M1, that term goes to 0. And I end up with acceleration is 0. Oh, that's interesting. M2, same as mu k times M1. M2, same as mu k M1. See, I derived that earlier as a special case. So you can see why analyzing in symbols gives you insight into how the system operates. Okay? So that's all I'm going to say about solving this particular problem. In summary, I would say that F equals ma, right? Net force, the forces causing the system to accelerate, minus opposing forces causing the system to slow down. That's the net force is the mass, total mass of the system times its acceleration. Okay, let's see how we did. We are up to 8 minutes and 27 seconds. I can do more. Let's do it. All right, I want to tell you about this. If you want to find the tension in the system, here's a quick recipe. You break it down. First, you find the acceleration of the system, like you know how to do now. And then you notice that the acceleration of mass 2, that's the hanging mass, is the same as the acceleration of the system because it's part of the system. So in the end, if you isolate M2, as I do in my diagram, you'll get a path to finding F sub t. Notice that in my diagram, I have F sub t pulling up, that's the tension in the string, and Fg pulling down. There is a big caution flag here. F sub t is not necessarily the same as F sub g. You're so used to looking at static equilibrium problems, you might jump to that conclusion. It is not true. Right? That hanging mass is accelerating, so those forces have to be unbalanced to get that acceleration. And that is how we look at tension in the string inside of a pulley system. Now, it's probably about 10 minutes now, 9:43. Should I keep you after class? Yeah, I have a bonus thing. I want to show it to you. And I could end at 10, but do you really want me to end at 10? It's 9:54. Yeah, I'm not going to sign out. I have to show you elevators because this is going to come up, and I don't have a special topic on elevators. So check this out. This bonus is how to solve an elevator problem. It's actually quite straightforward. This is the time where all of my earlier admonitions to know what object you are studying comes into effect, because you could choose to write a force diagram of a person, I'll explain these in a minute, or an elevator box, right, and an elevator shaft, okay? If you choose to do a force diagram of the person inside the elevator, you have a force G, the gravity force pulling down on the person, and you have an F sub n, normal force, pushing up. So you can even feel that. Look at my point number 2 here on the list. F sub n it's pretty much what you're feeling on a bathroom scale if you were standing on it. So if you feel heavy, your F sub n is big, and that's also something called apparent weight. So a bathroom scale is nothing more than a device for measuring F sub n. Okay, everything I said is what happens if you choose to make a force diagram of the person. On the other hand, if you make a force diagram of the elevator box itself, there's maybe a cable pulling up or some kind of a piston pushing up from the bottom, and there's F sub g, the whole weight of the elevator itself, and maybe there's a rider pushing down. It's a different force diagram. So make sure, back to point number 1, know which object you're studying. Make sure when you draw your force diagram, you're consistent in your illustrations. I hope to do more about elevators in a future video at some point. It will probably not be part of the series because I'm strictly looking at things that we've done as presentations in my honors physics class. So that was done more as a lab, and so it's an idea for a whole other series. But I've kept you after the bell. It's 12 minutes and 19 seconds. Go away, go home. Thanks.